case, guys, you guys are, I don't know if you guys are recording, but in case, guys, you guys are out on one day, guys, I mean, again, I'm recording every class, so, so if you guys are out on like one day, or if you want to go back and look at something, then, this will be available for you guys, okay? All right, let's take a look at, guys, the chapter, atomic structure, guys. So, who never took chem, like ever? You guys all took, you guys have a background in chem, all of you guys, right? So I don't have to explain to you like the bare basic, right? I don't have to explain that, right? All right, so let's discuss. I mean, I will not like go too fast or too crazy, guys, but I'll try to point in like really basic stuff. Okay, so first thing first, guys. Again, so. I'm going to try out one more thing. One page. Yeah. This is a reading, guys. The question homework, guys, will not be based on this. Will not be on this thing. Second, guys, I gotta print out your periodic table. Okay. Okay. All right, guys. So let's do some basic exercise here, okay? So when you guys get your periodic table, guys, first thing first, let's try to learn how to read this thing, okay? It's carbon here, 4.011, okay? I think it's 6 here. So I'm sure you guys know how to read this, right? Basically, what it represents. So this is what we call, guys, atomic number. Okay. All right, so periodic table, guys. So atomic number will define which element it is. Carbon is always 6, okay, and this is always what, guys? Number of protons. Yeah. So it doesn't matter how many electrons or neutrons they have. If they have 6 as atomic number, which is number of protons, they're always carbon. Very simple, like, dude. This is like 6th grade stuff, right? So now, what about this one, guys? This is what we call, guys, what? This is so depends on the teacher, okay, how they wanna like terminology wise for this one, okay. So sometimes they call this atomic mass, okay. Sometimes they call this, sometimes they call it weight, atomic weight, but this is actually mass, okay. So it's called atomic mass. So keep in mind, guys, just so one thing to understand, why is it that there's a decimal point, okay? So when you look at carbon, so in terms of how they write it, guys, like 6 here and 12 there, okay? So here, this is in terms of like how they write this. There's a carbon with 6, this number, this is the atomic number. This is what we call mass number, okay? So mass number is what, guys? Mass number is number of proton plus number of neutrons, right? So you got this. You also have this. You also have this. Okay. So if you look at this, guys, mass number is what, guys? It's number of proton plus number of neutrons, right? So as you can see, guys, this guy is what? So mass number is what? Number of proton plus number of neutron. That's what we call the mass number. Okay. So this is what they call, guys, like, oh yeah, carbon come as well. C12, C13, C14. Okay? So as you can see, guys, okay, so they have a different number of neutrons for carbon. So, and again, like it'd be 12 as a mass number, 13 as a mass number, 14 as a mass number. Okay? But now, atomic mass, what's atomic mass, guys? It's an average of the abundance of C12 and 13 and 14. So as you can see from this, what happens, guys? Oh yeah, like in nature, abundance perspective, they're 99% or more is what? C12. Okay, maybe a little less than 1% of these two guys are available. So that's the reason why when you weigh them up, what happens? It becomes what? 0.011 becomes what we call the atomic mass of carbon. Okay, that's what the number is. Okay, so now, so that's why it's not what clean cut 12, as you can see, as atomic mass perspective. So now, one thing to understand, guys, here, units. So they call this what, guys? Like 12. I'm just gonna say 12. 12 AMU. Okay. So one carbon atom. Okay, one carbon atom. Its mass is what, guys? 12 AMU. 12 AMU is what? Atomic mass units. Okay? Like food, like atomics, right? So as you can see, guys, okay? I mean, it's the number perspective, okay? One proton and one neutron, same mass. I mean, they're a little different, but they're what equal to what? 1 AMU. The mass is 1 AMU. Okay, so now, carbon atom, guys, the carbon C12, okay, is what? Okay, so they got 6 protons and 6 neutrons, which is what? Because add up to what? 12 AMU. Okay, so one carbon atom is what? 12 AMU. Okay, it's not that bad, right? Atomic mass units. This is a unit, okay, for a mass. Okay, it's a very small, tiny mass, right? Because the atom is really small. So now, any questions? This is like nothing new, right? Nothing too fancy. Okay. So one thing to understand is what? So the scientists, right? So you guys probably heard this and know this and all, guys. The scientists were, you know, like, okay, so AMU is such a small unit. Okay, we need to utilize something because atom is such a small thing, right? So we need to have a larger unit. Okay, and that is, guys. So we know that one atom of carbon equals what? Equals to 12 AMU. Okay, because again, the mass, I mean, you guys all know, the mass of the atom, the AMU is based on what? Carbon atoms, right? So what they want to do, okay, is what? We want to have a term where this equals what, guys? 12 grams. They want to use grams. Okay, so AMU, man, like I don't know what he said, they want to use grams. Okay, so they are trying to come up with this term. Okay, so whatever that term is. So I actually did solve this like create equation for this yesterday. I don't want to mess it up. Give me a second, guys. So basically, guys, what I did is, so like what that term is what? What's the term, guys? The term is what? The mole. Okay, I'm sure the term, right? The mole, right? I tell you guys, your mole, like they did it backward. Okay, so like I need to have 12 grams. Instead of AMU, I want to use grams. Okay, so if I have one XXX, you know, 1 mole of carbon, that becomes what? That many grams. So basically, guys, so the question is what? How many carbon atoms is in 1 mole, right? That's a question you have to ask yourself, right? So, I mean, you all know this, right? Like the Avogadro number, you guys all know this, right? So that number came from what, guys? So the conversion is, you have to know this, fine. So 12 grams of carbon. I want to figure out how many atoms you have, right? So the conversion is, so basically what I did here last night is like it's a 1 atom of carbon is 12 AMU, okay, AMU. And now 1 AMU, which is a mass of a single proton. I mean, you don't have to, I don't know, for you guys, I don't even think for AP Chem, you have to know the mass of a proton or neutron, okay? It might be given to you. I will not see the same thing for if you're talking about physics here, but its mass is 1.67 times 10 to the power of negative 24 grams. Okay? I memorized this number actually. Okay. So now if you look at it, guys, so in terms of unit perspective, okay, not that you have to really know it, I'm just showing you guys where that number came from. So if you look at it, guys, the grams cancel out as units, AMU cancel out. So you will have in terms of atoms of carbon. So if you solve this, you get what? 6 times 10 to the power of 23 atoms of carbon. So I'm just saying, okay? Where did that Avogadro number came from? Like, oh yeah, like I know that 1 mole, this is equal to, okay, universally is what? 6 times the power of 23 atoms of carbon, okay? Like, dude, you guys should know that, right? From doing the regular chem, right? So where did that number come from? Is what? They did it backward. Okay, so they said, okay, so I need this term, and which will turn to grams instead of AMU. So, and that's what? That number. So that's what they call Avogadro number. So a lot of times they'll say, oh yeah, you have this, is what the molar, they call this what? A molar mass. Okay? As what? Molar mass is what? When you got 1 mole of the carbon, what? Becomes a 12.011 grams, not AMU. Okay? So have a history on guys, like have to understand where the history of what? Where they came from AMU versus grams. So basic, like understanding of the term mole. So again, if you guys have periodic table, guys, we should bring it. Yeah, maybe we should bring it. So for example, guys, when you look at this, for like again, molar mass, atomic mass is 12.011 AMU. Okay, but molar mass is what? Grams. Okay. Any questions on any of this? Any questions, concerns? All right, so let's talk about some guys, some basic atomic structures. Okay. So, okay, so since you guys are okay with this, I'm sorry, your teacher's not gonna teach this, guys. Like it's not like a lot of times it's not in the readings. Okay, so like it's between you and me. Okay. All right, so. So the atoms, right? The history of atoms, right? Like something that I really don't want to talk about, like only one, it should be only once a year thing, okay? So the history of atoms, okay? So probably heard guys a guy called Dalton, okay? Dalton is the first guy. Some teachers talk about it, some teachers don't, okay? Dalton. So this is the year-wise, guys. It's around what? Early 1800s, okay? So, yeah, this guy, just so you know, from what I know, it's an English philosopher or something. Okay, nothing to do with chemistry, nothing. Okay, so what did this guy say, guys? What did this guy say? This guy came out and said, well, okay, so there is something called a small tiny particle atom. Okay? Atom is what, guys? It's the smallest particle you can break down into. So, dude, basically what he did is what? Okay, so he didn't have phone back then. So I have a paper, okay? I'm gonna break this in half. I'm gonna break it in half, break it in half, break it in half, break it in half, until what? I can't break down any further. That's what they call atom. Okay, indivisible particle. Okay, so that's what he said, right? Okay, so atoms are what? You can't you can't break further. Indivisible. Okay. So yeah, dude, indivisible, is it correct statement today compared to 1800, guys? Yeah, but what do you think, guys? No, this is wrong, because why? Atom, you can divide, okay? Like, dude, just like a what? You can take the electron out from the atom, right? That's like you're dividing an atom, because what? You're taking the electron out, right? So this is not correct, okay? This is, guys, it's not correct anymore, okay? Because they're saying, I mean, also even what, guys? We have nuclear decays, okay? Like, for example, guys, what? We got like C14, okay? The nucleus gives it away, okay? Like, for example, a neutron or something like that, okay? Or like, the electrons, right? What we call the particles of what? The electron particles, right? The beta particles. Turns into. Okay, so so is it truly indivisible? I don't think so. Okay, so no, I don't think. He said it back then, but I don't think so. Okay, what about 3 guys? So he also kind of mentioned. Okay, so this is also incorrect as well. Okay, so he mentioned. Okay, so there are elements. Yep.
What does that say?
Which one? Circle?
Like all the way on the right.
Oh, this one?
Yeah.
That's 14, 7. So carbon going into decay turns into a nitrogen. Okay, so this, you know, this is fine. So I'm explaining basically what happens is the process where this is where, like, you should probably hear like radioactive decay, right? C14 turns into like something else, right? So this is what happens, a beta decay. Okay, so it releases an electron, which is a beta particle, and turns into what? Nitrogen. It's fine. This is not something, I'm just example perspective, that's what I'm trying to show. And the other thing that this guy said as well, guys. So there are elements, right? There are, how many elements? He didn't know, like, oh yeah, there are like 100 elements. No, he didn't know that. So there are elements, and what he mentioned as well. Every element, okay, if you have a same atoms of the same element, they must be exactly the same. So, meaning, for example, guys, imagine this, right? Carbon atom, right? So carbon and carbon is the same, right? But he's saying, oh yeah, they should be same all the time. That's not true as well. So they kind of mentioned, okay, so atoms are the same element. Should be the same, okay? Should be the same. Yeah, that's what he said. So what that means is what, guys? Okay, so we know that is not true because what? Dude, we got what? Just like what we talked about, we got C13, C14, and what? C12. Okay? These are considered the same element, right? Because what? They have the same number of protons. But what? They have a different number of neutrons. That's why they're not the same elements. Okay? They're the same element, but they're what? They're not exactly the same from each other. So this is also, you know, not so true, okay, as we know. But now he also mentioned something, okay. So this is basically, I don't know, to me, man, this is just a repeat of something other scientists mentioned, okay, which is he mentioned about compounds, okay, which is a correct statement. So what he mentioned, okay, or kind of reiterated as well. So definite proportion of a compound. Okay, that's what he said. Definite proportion, which means if you look at it, guys. So if there are two elements bond together in a compound. So for example, guys, H2O, right? So water is a binary compound with what? Element, hydrogen, and oxygen. So, which means when you create water, okay, as a compound, it's always what? Always. It's a 2-to-1 ratio. Always. That's what they call a definite proportion of a compound. Okay, and that still stands true, right? But he also mentioned what, guys? A multiple proportion. So, guys, the multiple proportion is what? Like, dude, think about it, right? If they bond together, does it always becomes water, guys? Always water, guys? I don't think so, right? This can be also what, guys? H2O2. Right? So hydrogen peroxide, for example. Okay, so you say, yeah, it doesn't always. So when this compound creates 2-to-1, but it could be what? There could be multiple different ratio of different compounds. Okay, this can be 2-to-2 ratio or 1-to-1 ratio. So that's what this guy said. Okay, that's about it. Okay, like how far can you go with this? Okay, as a English professor or English philosopher or something. Okay. So it's more on like I think like I don't know, just a theory. A lot of theories. There's nothing you can prove on this, you know. But that's the term. So term atom is not something, guys. Okay, it came up like on this time. But I think the term atom first came up like way back. Okay, but he kind of mentioned like defined. Okay, indivisible particle. That's why we talk about this guy. Okay, so it's all happened, guys, early 1800s. Okay, and next guy. So again, like the reason I mentioned this guy is we have to talk about it, guys. Not really, but some of these guys I've seen on the AP exams. That's why I'm talking about this, because, you know. So some of these guys. So guys, the next guy, which I don't also think, guys, is really important to like, spend so much time on, the guys, is Thomson. So Thomson's model. I mean, it is important, guys, but we know for a fact it's incorrect. Okay. So Thomson's model is what, guys? This guy created a model for the atom. Okay. He said, like, a model looks like this, atom looks like this. Okay. So it's what they call, guys, plum pudding model. Okay. So plum pudding, guys. Okay. It's like, so basically is what, guys? I mean, it's like a It's like a muffin. Okay, so if you guys look at this, guys, it's a muffin with little raisins in there. Yeah, so the muffin portion is actually positively charged. Yeah, and like so, and then also what the little particles inside is what they're electrons in it. Okay, these are like little tiny electrons in it. And that's basically, guys, what we call a plum pudding model. And these guys don't move. Okay, it's a little what, like specks in there. They don't move around. That's what Thomson's model is. So basically, what's the significance of it, guys? Is what? Electrons. He's like, oh yeah, there is a subatomic particle, something we call electrons. And so that bread portion is positively charged, okay? And the little tiny electrons are what? Negatively charged. Okay. And the way he found out about this, guys, it's basically, guys, he used, guys, the electrodes to find this out. But again, that how they figured out, guys, it's not on it again. Okay? So this plum, yeah, so keep in mind, okay, this plum pudding, I tell you guys, is back in time is really widely accepted. Like they say, oh yeah, that's the guy. Like the textbook, right? If you guys look at textbook, the atom like what? Like electrons like revolve around, guys. Not like revolving around like that, but like when you think about atoms in the textbook, there's like a shape that you get, right? Yeah, back then this is the shape that you got, plum pudding. So this is somewhat, guys, like the thing back in time, guys. But again, this was, of course, guys, again, not the stuff that we discussed in the slide. Here's a guy called. This gets a little harder, guys. By the way, as we get to recent ones, guys, for AP Chem, it gets a little harder, by the way, just so you know. So therefore, guys, what did he say? This is what? This is the guy that mentioned what? There's a guy, guys, the name is, I think, a Chadwick. He's the guy that figure out like the neutrons and stuff, guys, which we're going to discuss. Nucleus, okay? So what do you do, guys? Gold foil. So basically, guys, I mean, gold, and so too, like if you guys look at the periodic table, guys, gold is what? Gold is elements, which is AU, number 79. Okay? So what he did was what? Gold is being an element. Okay? So basically what he did was he had a very thin slice of gold. What happens? He shot alpha particles. So alpha particle is what, guys? Alpha particle is, it's a helium nucleus. Okay? That's 2 plus charge. So 2 proton, 2 neutrons, guys, alpha particles. Like he shot it through the gold foil. Now imagine, guys, right? If you guys have a plum pudding model, so imagine like you guys like when you do a lab question, guys, you guys have a hypothesis and stuff like that. Like, okay, so this is what I think, hypothesis, if I shoot this guy, what's gonna happen, and then you do the experiment and there's a result. So if you think about it, right? If we have a gold foil of plum pudding model, okay? What do you think? What do you think? You got this, is what? You think about the atom as little muffins, okay? They filled up the space, right? And imagine you shoot something through it. Like the analogy is what, guys? You have a wall, you're shooting what? Like, bullet into it. That's basically what the analogy is here. So what do you think will happen? What do you think, guys? Well, as these guys go through, what happens, guys? They'll put a little hole in there. Isn't it? The muffins are what? Penetrate. That's what the expectation was, right? Did that happen, guys? No. What happened, guys? All of it went straight through. There's nothing happened to the gold foil. Imagine that 99.99% it went straight through. Nothing happened this time. Okay, like what happened, right? Very small portion deflected. It's not straight. It's like deflected, maybe deflected back, whatever. Okay, but this thing's intact. That's actually what will happen now. Okay, so that's where they start to think, what? Oh, this is not the way. That's not it. And what? It's what? Atom is. Why do they go through what? Atom is and what? Why do we have some deflection to what? There's what? A very dense particle in the middle of the atom, which is called the nucleus. That's where the term nucleus came out from. Okay, so if you look at it, guys, an atom is like this, right? Stacked together, the gold atoms. And now they shot the alpha particle. What happens, guys? It's mostly empty. They went straight through like this. Okay? And if it came near the nucleus, what happens, guys? Deflect. Okay, that's where the deflection came from. Like 0.1% or something. Okay? So that is the what Rutherford did. Okay? Nucleus, mostly empty, but there's a dense positively charged particle in the nucleus. Okay? Based on the behavior of the particle, it seems like it's repelling. That's why you figure that's positive charged nucleus. And this is where, guys, it's now from here. It's all about what, guys? Electrons. Okay? It's all about the electrons from here. Okay. So, like, keep in mind, guys. Okay, this is, guys, or what? Every single thing is what, guys? Either late 1800s, guys, or what? Early 1900s. This is not, dude. This is only what, like, most like what, 100 years ago. Yeah, this is 100 years ago. Okay, like how long is the human, like, like the civilization? Like, dude, this is only 100 years ago. Okay. And now, guys, this is where, guys, it gets a little tough. Okay, the electron. So this is where the entire class discussion will be, I think. Okay. So, so guys, please listen carefully now. Okay. More smart. So before we get into this, okay, let's talk about a few things. First thing first, guys, for AP Chem, and I'm not kidding, guys, you gotta know this. Okay, so you have to know a little bit of electromagnetic waves. Okay. Like some of the kids, like I remember, like 3 years ago, like one of the kid in here, guys, like they argued, like, well, what do you have to know this? It seems like this is like physics. I mean, dude, like you gotta know for AP Chem. Electromagnetic waves. So, so electromagnetic wave, guys, is nothing fancy. Okay? This is what. This is the wave that's considered as well, like visible light, okay, infrared radiation, like radio waves and stuff like that. I don't know if they have it here. I'm not sure. Like X-ray, cosmic rays, like UV rays, and that's all part of what we call the electromagnetic waves, okay, including the visible light spectrum, okay, like red light and blue light and stuff like that. So, what you have to understand is there's a few equations you have to know. Okay, this is I tell you guys, some kids, man, I don't know, it takes them a while to learn the equation. Okay, so the equations for any wave, it doesn't really apply for this electromagnetic wave, guys. Okay? For any wave, this equation applies. Speed of the wave is equal to wavelength of the wave times frequency of the wave. Okay, so wavelength and frequency. Okay, so again, speed of a wave, okay, is equal to what? Wavelength. The speed of the wave, guys, I'm gonna say velocity, d. D is equal to, guys, wavelength, lambda. Lambda is the symbol, guys. Okay, lambda is a symbol for wavelength. Okay, frequency is lowercase f. Sometimes they use a different, like symbols here, guys. That doesn't matter. Okay. So velocity of the wave is equal to lambda times frequency, wavelength times frequency. Okay. So this applies for every wave. Okay. So what the hell is wavelength? What the hell is a frequency? Okay. Do you have to know that, guys? I really don't think so, but okay, whatever. Let's talk about it. Okay. So wavelength. So waves, guys, from electromagnetic wave perspective. So we're not in physics right now, guys. I'm not to discuss like longitudinal transverse wave and stuff like that, guys. So wave, guys, again, like I don't know if you guys know trigonometry, guys. Wave looks like a sine curve. Okay, that's what wave looks like. Okay, so wavelength is what? Yeah, wavelength of what do you think, guys? Is what? The length in meters of one full wave. That's what we call wavelength. So, like, dude, like wave looks like this, right? Like wave looks like this. Okay, and wavelength is what, guys? Distance of the one full wave from here to here. That's what we call the wavelength, okay? And now, what is the frequency? Okay, so before that, guys, the wavelength, the unit should be in meters. Okay? Meters should be the unit, guys, like meters, distance. Frequency. This one is a little tricky, guys, frequency, guys, okay? definite. So this is, guys, I tell you guys, okay? What was that? Like, it was AP Bio, right? AP Bio. So this is, they, in AP Bio, okay, in one of the chapter, frequency refers to percentage, okay? You know, absolutely incorrect, guys. That is not the right one. So frequency, okay, the terminology should be what? So the waves are like, passing through this way. So which means that this is the point, right? So just pick a point. Yeah? Waves are going from one point to the other. Okay, moving from to the other, right? The question is, the frequency is how many waves pass this point in 1 second? Okay, in 1 second. So if two waves passed in 1 second, that's what the frequency is what? Okay, that's what frequency is. How many waves pass in 1 second? So the unit for frequency is hertz. Okay, like the car rental place, hertz. So hertz, right? Hertz is equal to 1/second unit. Okay, 1/second. Okay. So hertz is 1/second. Okay, I'm sure you guys like, I don't know how much of the stuff you know as speed is what? The velocity speed is what? Meters per second is unit. Okay, so when you multiply wavelength and frequency, you get what? Speed. That's meters per second. So this is for not only for electromagnetic waves. Electromagnetic waves, what guys? Like visible light. These are the waves, guys. But now like water wave, sound wave, every wave that you guys know, this equation applies. Speed of the wave is equal to wavelength of the wave times the frequency. Okay, that's the like most basic equation you have to know. Okay, for this chapter. And you tell me, guys, okay? So, I didn't learn this. Yeah, you gotta learn this soon, okay? And now, for electromagnetic waves, which is like visible lights and infrareds and UVs and all, speed of light. Yeah. So for electromagnetic waves, okay? Speed of the wave, electromagnetic wave, is equal to 3.0 times 10 to the power of 8 meters per second. Yes, I'm sure, I don't know, man. You probably heard this, like speed of the wave, guys, sometime, guys. I'm not sure when. Okay, like the speed of light, right? I'm sure you heard that, right? That's the speed. So, like I'm sure. Oh yeah, light moves fast, right? Like light years. You heard that, right? So that speed is not only visible light, but as well it could be UV, infrared. Okay, it could be what? X-ray. Okay, so radio wave. The radio wave that, like, the FM radio wave, guys, like, you probably like the car radio. So all, like, microwave. So these are all, okay, visible light, they have the same speed, okay? They all fall under what we call electromagnetic waves, okay? And they have what? Same speed. Yeah, so one thing to watch out for, okay, is this. So you guys will learn this a little more in physics, okay? When you got, so not even physics anymore because this is one physics. So in the AP chemistry on the reference table, okay? So on the actual AP chem reference table, guys, they say this as 2.99. Yeah, times 2.99. So I do not think you'll get it wrong for putting 3.0. Yeah, I don't think so. But if you want to be on the safe side, guys, then yeah, use 2.99. So it depends on, like, some kits like pointed out I think last year, but I don't think it really matters. But I don't know. So why is 2.99, guys? So I mean that's 2.99 in the air. The speed is 3.0 in vacuum. Okay, but this is in, guys, in air. So for when a light wave enters like the medium, they tend to slow down a bit. Okay, that's probably the reason why they made it like that, kind of slow down. But it's very minimal, like, stuff. I'm not really concerned about. So one question, okay, for any electromagnetic wave, okay, so this is sometimes known as c. C is the speed of light. C is equal to lambda times frequency. That is something that you need to know, okay, the equation perspective for electromagnetic wave. And the c is what, 3 times the power of 8. So you can say, oh yeah, wavelength of this electromagnetic wave is presented by 3 meters. Okay. Person can ask you, oh, what does the frequency? I mean, like, how easy can the answer question be, right? So 3 times the power of 8 meters per second is equal to, guys, like 3 meters as a wavelength times frequency. Yeah, frequency can be calculated relatively easily. Okay, but now you guys have to get the hang of what? Make sure you watch the units. Okay, meters per second, meters. Okay, so then I can get the frequency in hertz. So you guys have to have the hang of, guys, now watching the units as what they're given. Okay. So meaning, guys, if you're given, for example, kilometers per second, you got to convert it to the meters per second to make them. Okay. That's one equation you have to know. Okay. So yeah. And the other question you have to know, guys, to understand the Bohr's model is, and this equation, guys, I'm going to give it to you right now, only applies for electromagnetic waves only. Okay. The equation is energy of these waves is equal to h times f. Okay. Planck's constant times the frequency of the wave. That's the energy of the light wave. Okay. So energy of the wave equals to, this is a constant. Okay, it's a constant number. It's called Planck's constant. This is the frequency. So so you can write it down first. Okay? I'll give you the Planck's constant, by the way. Okay, 6.63 times 10 to the power of negative 34. That's a number. Okay, it's a constant. So I memorize it. Okay, it's good to memorize 6.63 times 10 to the power of negative 34. Memorize it if you can. Okay, this is in joules, by the way. Okay. So let's talk about this. Okay? So not too crazy. Okay, what this equation is. So, yeah, you guys all know, right? So based on what we talked about, you guys all know, guys, from the equation, right? Higher the frequency, greater the energy, right? So, yeah, AD by, right? UV ray, can what? UV ray, right? Like sunlight, UV ray, right? Can what? Can damage a DNA. Okay? And what? Oh, causes what? Causes mutation. Okay? It can what? Splice up a DNA, okay? And what? Cause mutation. How? Yeah, because UV ray can do this. Okay, can infrared do that? Can infrared do that, guys? Like infrared is what? Infrared. Yeah, you get infrared. Yeah, this is infrared. The stuff that comes out of this, guys, it's infrared. Okay, so if I do like, would you guys like? Oh no, like you guys do that now? Why? Infrared is what, guys? Has a what? Low or smaller frequency. Okay, this one is what? A greater frequency. Okay, so why was like this guy so damaging? Because what? Dude, what? It's if you have a high frequency, it has a greater energy. If it has a greater energy, what? You can do more work. Okay, it can do more damage. Okay, so it's like, for example, so so UV ray has a high frequency, infrared has a low frequency, which means what? Yeah, this has more energy, which means what? Once it gets to DNA, it might cut the what? The bond, right? So that's what this equation is, okay? So the energy of these light wave, okay, depends on what? Frequency. But now the intent of this equation, okay? The guy named Planck, so it's a lot more than what I just talked about, the equation, okay? So that's the intent of the equation, right? Like, yeah, energy, the photon, energy of the light, depends on this guy, frequency, right? So the purpose of this equation, okay, why do they call this equation? What is this? So to explain that, I don't know, it depends on the teacher, your school guys, and they might talk about it, but I don't know, man, like, depends on the kids if they understand this, guys. 요게 why they talk about it, guys? Because what they call, guys, quantized energy. So that's basically what this equation is for. Okay, quantized energy is a Planck's equation. Okay, the Planck's constant, Planck's equation, right? So what it means is this, okay? Energy, okay? So you cannot give energy, transfer energy in any continuous amount. It must be quantized. By how much? By this much, okay? So what it means is, if I give you guys money, for example, okay? Can I give you guys like a bill perspective? Can I give you guys a zero? Can I give you guys half a cent? Can I give you guys? So I'm gonna take money out. Can I give you guys half a cent? I can't, because why? The monetary system is based on what? Based on 1 cent. That's the smallest I can give you guys. Okay, as a quantized value perspective, it must be multiple of what? A cent. I cannot give you a fraction of a cent. Same thing. So in terms of the energy transfer perspective, it must be what? Quantized energy of this much. Okay, so I can give you this much energy. Okay, I can give you twice of that. Okay, but I cannot give you anywhere between the two values. You understand what I'm saying? So that's what they say, a quantized energy. Okay, energy transfer must be quantized value. Okay, of what? The Planck's constant. So it's like same thing, right? So if you guys have a little background, like charge of electron, or even mass of electron, okay? So charge of electron is what? Charge of electron is 1.6 times 10 to the power of negative 19 coulombs. Okay, that's a charge of 1 electron. Okay? And what's a charge of 2 electrons? 2 electron charge is what, guys? 3.2, right? Can you have 2.5? No, we can't. Because what? You can have what? Fraction of electrons. Same thing. And that's what this guy did. So do you have to know that, guys? I don't think so. I don't think you have to really go that far or quantize energy, Planck, but just have an understanding of where this one came from. Yeah. Because you probably hear the term a lot, the quantized term a lot today. Okay. So guys, what is this equation? Let's talk about the work model. What is this guy? We still talk about it because he's not wrong. Okay, this guy's not wrong. Okay? This guy's partially right. Okay, why he got it right? It could be based on a little bit of luck and whatever. Okay, so I think this guy's Danish scientist. I think if I'm not mistaken, guys. So. This is what he said. Okay, so we got a nucleus, it's all good, So we try to figure out where the electrons are at, right? So so nucleus is here. So basically what he said is what? Planetary model. So electrons circle the nucleus. Okay. So the protons here, electrons are what? They have a definite orbit like this. Okay, so circular orbit, like a planet, right? That's what it is. Electrons revolve around. Okay, that's what he did. Revolves around like this. Yeah, I mean, I'm sure you guys heard this, right? That's what this guy did. I mean, again, this guy did not propose a planetary model. The Rutherford did actually, but he took it to a next step. Okay. So I think, guys, if always the problem explaining, guys, with this, if you guys have a little bit more background in physics, this will be a little bit better, but that's fine. I don't think you have to go that far. So what he did is what? What he mentioned, and then what tested out is what? So there's a nucleus, okay, and the electrons revolve around, okay, in a concentric pattern, okay, circular orbits. And now they also have something we call principal intervals, energy level. Okay, just like how we talk talk about quantized energy like this guy. So what he mentions what? This is the energy level, okay, of the electrons where they can be at is quantized. Okay, so electrons cannot be found in between these levels. Okay, they must be on what? These designated quantum level. Okay, principal energy level. Okay. So, so there's a lot of physicists kind of try to counter his findings and like, okay, what the hell doesn't make sense, you know? But what he's proposing is electrons can be found at the first level, second level, third level, fourth level, and more, fifth and sixth and seventh. It kind of goes on like that, okay? And then why we still talk about him is because why? He provided an equation, okay? He provided an equation, guys, okay? So that's basically, guys, why we still talk about it. So like the probably guys, like the importance of this guy is from the equation, okay? There's a Rydberg, like, you know, the constant and all that stuff, he brought it up, guys. So what he did is this, okay? The energy of, this is a potential energy of the electron, okay? Energy of the electron on these levels, on this level, the principal level. So is equal to, so I'm gonna do this, negative 13.6 eV over square. People, I think, okay, I don't think, like, the equation, I don't really think it's in limit, but the idea, absolutely yes, okay? Like, there are several happening here, okay? So, I think if you look at so this is an EV, okay? The different energy unit, okay? That's how I remember this. But I think if you look at the text, the thing, it gives you guys the equation, okay? Energy of electron. Okay? So this is on page like 23, I think. So it's given as E is equal to, guys, negative 2.178 times 10 to the power of negative 18 is in joules, n squared joules. Okay. It's the equation, guys, okay? This is the nth principal energy level. I guarantee you guys, your teacher will talk about this. There's no question, okay? They will talk about this equation. So Planck, not Planck, I'm sorry. This guy, okay, Bohr guy, came up with this equation. He's like, oh my god, you know, no one came up with the equation for electrons. Now he did. Okay. So now, so this is basically, guys, how we came up with the equation. Okay. So let's talk about this a little bit, okay? And like, okay, so why is there a negative sign here? You know, that's something you have to understand as well. Guys, this is what they're saying. So this is basically, guys, the principal energy level, okay? And 1 and 2 and 3 and 4, okay? So this, I'm gonna say n is equal to infinity. Okay? So 5, 6, 7, like it goes up and it becomes infinity. Okay. Now, so just to explain this, guys, right? Between plus charge and minus charge. Okay? That's why I'm keeping saying, guys, if you have a little background in physics, makes it a little better. So if you look at this, yeah. If you have plus charge and minus charge, right? What do you do? What do you do? They attract. They try to what? Attract each other, right? Pull out attraction, right? But now, imagine, right? You are, let's try to separate. You try to pull this guy away. Okay, you move this guy up to here, right? To do that, what do you have to do? You have to what? Yeah, dude, this guy wants to come this way, but you're pushing this guy out, right? Look at it. What do you have to do? You have to what? Put work. You got to do work. Push it, right? Work is needed. Okay, to do that. And now, think about this, right? There is a term that you probably heard many times, right? Conservation of energy. You know that, guys? Heard that somewhere, guys? Yeah. I'm doing work. I put energy to put this cell there. Where did it go? That's like, where did it go? Oh yeah, it goes well. Potential energy. How much energy is stored in the electrons? So it's stored in there. Okay. Yeah. Because what? If I let go from here, it's gonna get there what? It's gonna get there with the energy. Okay? It's stored in there. Stored energy. Electrical potential energy. Okay. So the model of the story is what? Further away, a negative charge is the positive charge around, guys. Now, if you think proton is here. Okay, proton is right there. Okay. So now imagine, guys, right? The electron is here. Okay, the electron, one of them is here. So it's the same thing, right? The one that's further away, I mean, from like the equation, right? If you know the equation, guys, potential energy of two charges is what? A times Q1 times Q2 divided by R. That's the equation, guys, potential energy of the two charges. Okay, so again, that's probably where he got that, like, you know, equation from, like something from there. Okay. Not that you have to do this. It's fine. Okay. But now imagine, guys, right? You have electron on the first level versus the fourth level, right? Where do you have, I mean, so which electron has a greater potential energy? Of course, as we discussed, the one that's further away, which is what? The fourth one. This is at a what? Higher, greater potential energy. No question, further away. You understand, guys? So now, okay, so now, look at this equation. Does it make sense? Look at the equation. So based on what he said, E sub n, energy at the nth level, potential energy at the nth level is equal to negative 2.178 times negative 18 divided by n squared joules. Okay? Keep in mind there's minus sign. Okay? Yeah, imagine, guys, right? If you're at the first level, okay, n is 1. Okay, if n is 1, what happens, guys? The energy is at the bottom is what? Again, negative 2.178 times what? 10 to the power of negative 18 joules. Yeah, what about if you're really far out? What about you're infinity? What about that, guys? Infinity of what? What's that, guys? This is a big number. What would that be? What would that be, guys? Would it be what? So math, right? Like if the denominator is really big for a fraction, what happens, guys? Close to 0. You understand, guys? Right? Like, dude, like, oh, like big number at the bottom, guys? 0. So this will be what? 0 joules. So now, you ask yourself, guys, again, you got 0 joules at the top, infinity, this negative number. Which one has a greater potential energy? Of course, 0. 0 is a bigger number. Do you understand what I'm saying, okay? So the numbers that you got is what? 0 is a bigger number than what? A negative number. That's how the potential energy is being distributed based on the Bohr's equation, okay? So now what he proposing, or based on what he did, is what? If I have electron drop from the infinity down on the first principal energy level, electron was here, it went down there, okay? Which means what? Electron lost potential energy. What happens? It's giving off what? It gives off light. Okay, it was giving off electromagnetic radiation equal to amount of energy lost by the electron. Okay, so that's basically the understanding of the Bohr's model. Okay, so based on energy, like electron coming from the higher level to a lower level, and what kind of wave comes out, and measuring their frequency, he was able to map out what? Map out this equation. Okay, so make sure you understand what was happening here. Okay, and basically what he's saying is what, guys? If you look at it, guys, okay? So electron from the highest level to here, okay, so giving off some kind of light, okay? So this energy of this light is equal to what, guys? HF. Planck's constant times frequency, and he was able to get the frequency and figure out how much energy was this is, and that is equal to what? So that is equal to HF is equal to what? Changes of the potential energy of what? Electron. Okay, based on the equation. So you'll be asked, okay, to get the wavelength and stuff like that. So meaning, guys, for example, okay, so what I'm saying is, based on this equation, electrons dropped from N4 to N1. Okay, and the question on the AQ will ask you, your teacher definitely will be going over this in school. Okay, find the frequency of the light that came out when electrons dropped from the fourth level to the first level. You understand, guys? So this is a question that will be given, okay, and you need to solve. And I'm not kidding. This is something to know. Okay, so basically, what, guys? Okay, how do you figure this out? Okay, so energy here, potential energy. This is initial potential energy, final. Okay, and you have to what? Figure out the discrepancy of the two. Right? You know, so I'm not going to do it, guys. Numbers are pretty. For numbers, pretty big. So we're like So for example, guys, this is like, for example, guys, like some number, like I'm gonna just make up a number. So like maybe like -1, this is -3, okay, joules. So the difference is what, guys? 2 joules of energy difference, right? That much energy what is given out, okay, which is equal to Planck's constant of the wave times the frequency. And that is equal to what, guys? That's equal to 6.63 times 10 to the power of -34 times the frequency equal to 2 joules. Okay? And you solve for the frequency. That's what you do. Okay? So this kind of thing is something that they'll ask you absolutely no questions. Okay? So you got to like this is something different from your regular chem. Okay, that's AP chem. And this is gonna be my homework, guys. Okay? Like FRQ questions. And dude, I tell you guys, okay? Like every time, like once the AP exam, like your teacher might talk about it, might not talk about it, guys. But for like March, like when you guys have to get ready for the AP exam, like these are questions are there, and they have absolutely no clue. Like I have some students where like they don't understand a single thing about these stuff. So either they were not taught, or I don't know, they just forgot or something. I'm not sure. Okay. So basically what I'm saying, guys, Bohr was able to figure out, like, okay, so the equation and all, basically that's what he did, okay? So he figured out, okay, he excite the electron, make it come down, what energy comes out, what light comes out, able to figure out the frequency of them. So, so one thing that I know Jericho folks here, like, I don't know, some of them asked this, I think, last year, or year before, I'm not sure. So for this is Bohr, just so you know, he worked with hydrogen atoms. So he worked with hydrogen atoms only. Okay. So all this thing that the equation and all, guys, he used hydrogen atoms to get it. Okay. So one thing to understand, guys, okay, if electron drops to the first principal energy level, okay, it gives off UV rays. Okay, and we can't see UV rays, by the way. Okay, UV rays is something we can't see. And if I'm not mistaken, okay, this is called a Lyman series. Okay, this is in textbook, guys. I don't think Lyman series is fine. Okay, you don't have to know that. But the Jericho folks, I think, I don't know. Some last year they said teacher talked about it or something. I'm not sure. Okay. So I'm not 100% guys on this one. Okay. Like, but just so you know, like it gives UV rays, and then if the electron comes down to second level, the second principle, that's when they give off visible light. That's the light that we see. Okay, so like I mean, again, depends on how many waves can go down like this, guys. But in a case like this, guys, coming from here to here, like we can see what 3 different waves come down. Okay, so we see, you know, so as you can see, guys, so this is coming to the higher level. Okay, this is coming from the intermediate, low level. So this can be like red light. This can be like the green light. This can be like blue light, for example. Okay, something like that. So then you'll see 3 color bands. Okay, on the bright line spectrum. Okay. So keep in mind, guys. Like, make sure to understand, like, okay. This one gives off more energy than this guy compared to that guy. Okay. So the least energy is what, guys? Like one with the less frequency. If you have a less frequency, it has a greater wavelength. So again, just like what I'm saying, right? Energy of the photon is what, guys? Hf. Okay, and what? Speed of light is what? C times lambda. Make sure to understand what I said. So what I said is compare this electron dropping and this one dropping. Okay. So this guy right here, 3 to 2, they give off less energy. Okay, right? Like, think about it, guys. Okay. So less transition for that guy, which means what? Less energy meaning what? Lower frequency. Okay? Lower frequency means what, guys? Greater wavelength. The speed of the light should be same for all waves, right? So you can, like, dude, like I tell you guys, okay? You can say this one should have greater wavelength and shorter frequency compared to this guy for sure. Okay, you guys understand what I'm saying from the equation that we talked about. Okay. If you guys like, oh, like, dude, I don't get it, you gotta let me know. Okay, like, can you repeat that again or something? You gotta let me know. Because like, this is something you guys have to know, guys. Is it like absolutely like important like 100% of the time? No, like it's a hit or miss. You might get questions on this on the AP, you might not. It's not every time thing. But if you guys go to school, the first thing they do is this guy. Okay, these things. Any question, guys? And now, so if the electron drops to the third level, guys, it gives off infrared radiation. Okay, infrareds, guys. Again, it's a low frequency, high wavelength, guys. Not that damaging, by the way. Okay. So basically, that's what Bohr's model is, guys. Okay, quantized energy level. Okay. But why do you think a problem is with this? Now, what do you think? I mean, is this like correct thing, guys? Is this the right thing? It's not the most up to date one that we have. So the question with these, so I don't think you won Nobel Prize for this as well, because this is not like there are a lot of oppositions on this, by the way, because physicists don't think it makes any sense. So the first question they asked is this. So the guy, so this guy, the physicist asked the question, right? Electron, why does it not go into a nucleus? Right? Like imagine, right? So if this is positive charge, negative charge, what happens then? I mean, so why would it not hit the nucleus? Like so, okay, why is it circular motion? Why can it like spiral down to the nucleus? That's what they asked. A valid question, right? So, and this guy said, well, okay, so they have what? Specific quantized energy level they should be flying in, and between or anywhere outside of this revolving zone, electrons cannot be found there. That's what he said. Okay, so like okay, physics perspective, that is not a valid statement. Okay, physics, like these people like what? They study the motion of the object, like forces. Like okay, so why isn't this happening? Is the based on Bohr's response like absolutely not. Like that's not the response. So that's one, right? And also they talked about okay, so the equation that they provided, right? The equation for the energy of potential energy of the photon, right? It doesn't work anything other than hydrogen. So if you use helium or like lithium or any other atom, the equation doesn't apply. The equation is what? No good. So I mean, like, dude, there's some stuff that's incorrect about this. Okay, and the quantized energy level also as well. Like, okay, so the shell, first shell, second shell, third shell. Like it's why. So there are a lot of like questions physicists asking. Like, okay. It's still, being asked. Okay. So I think that's the limitation of the Bohr model. Bohr's model is the circular motion, okay, with what they call quantized energy level. But why we still talk about is what? The equation. We're still talking about it. Okay. And from here, it gets pretty complicated. From here, guys, like it gets a little more complex than the stuff that we just discussed. So, any questions, guys, before I move on? From here, any questions, guys? Okay, so keep in mind, guys, the equations. I tell you guys, the equations that we talked about, guys, do not forget them, okay? So now, guys, this is very recent. Like, dude, like, I mean, like 1900s to 1950. This is where this is all happening. Okay, like it's not like way back. Okay, dude, like my parents, like my grandparents were born this time. Okay, so like it's around that time. Okay, so look at it. So and all of this is also, guys, like the result of all this is what? Atomic bomb. Okay, so yeah. So basically the next piece of this, guys. So to understand this, so it's all about now is all about the electrons, where they're at, and how they behave, and where they're at. That's all. Like that's what this is all about now. Okay, so basically, guys, what they did now, okay. So your teacher will definitely talk about it, guys. Einstein, okay. So Einstein. So basically, this guy is something that we want to discuss. So I mean, not directly related, okay. So what he I think Einstein got the Nobel Prize by not the E with NT delta squared, not this guy, not even for the relativity. Okay, he got it for this one. So what Einstein proposed, okay, is light is a particle. Light acts as a particle. Okay, so it's called photoelectric effect. That's what this is. And listen to this, guys. Okay? So basically, what he did is this. It's something similar to the gold foil, completely different idea. Okay. So basically, what he did is what he shined. This is a metal plate. It's a metal plate, and he shined light into the metal plate. Okay. And now, so basically, what has occurred is what, like, basically what, guys? I mean, so this is electron. Okay. You put light into it, like the opposite process happens. The electron can what? Get ejected. The light electron will go up. Okay. Higher level. So if light was put into metal plate, what happens then? Electron gets ejected at some kind of speed with kinetic energy. Okay. So that's basically, dude. It might sound very simple. Oh yeah, dude, I could have done that like last year. You know, just I got a metal, like shine light. Okay, like that's a little prize right there. You know, but the understanding idea. Okay, that's where this comes in. The light was put in. Okay, hit a metal plate, and energy comes out. So what he found is what? So basically, what he found was okay. So light was acting like a particle. Okay, like dude, like there's a ball. You hit that ball with the other ball, and it gets what? It gets what? Pushed out, right? So that is some kind of behavior that he's seeing. Okay, which is what we call a photoelectric effect. Okay, so light, so energy of the photon E is equal to hf. Okay, so like, okay, so light will shine through the metal plate. Okay, what happens, guys? Okay, so basically, okay, this is how much energy was given to the metal plate. Okay, and again, what happens, guys? In order to take the electron out, you gotta put energy in there. Okay, electron is being pulled out, energy is put in. That's an amount of energy needed to remove the electron is what we call the work function. Yeah, it's called the work function. That's what amount of energy needed to remove the electron. So okay, so if this is like energy was given like this, work function, okay, the remaining energy comes out as the energy of the kinetic energy of electron. So that's the main idea. So now what he did is this, okay, he shined the light with greater frequency. Okay, then what do you think will happen? So same intensity of light, okay, same amount of light but greater frequency. Okay, what do you think will happen? So same like one number of waves here. What do you think happens? So you do not get more electrons. So imagine thinking like this. Okay, I threw the ball, okay, with greater speed. Okay, then what will happen? The ball that's getting ejected from the wall is what? Going out at a greater speed. So I don't get more balls outside the wall. So what happens, what, guys? I mean, so again, you get an electron with the energy. So basically, like, what he's doing is this. What he's doing is the equation is, so not that like you gotta really go crazier, guys, is what? The equation is the kinetic energy of electron is equal to what? hf minus the work function. So it's a 1-to-1 ratio. So he start to call the light as what we call light particle, which is what we call the photons. So 1 photon, 1 electron ratio. Okay, the 1 photon cannot take out 2 electrons here. Okay, so which means what? It's acting like a freaking particle here. Okay, so that's why you keep on mentioning what? The term photon. That's what Einstein's photoelectric effect is. So, and that's the equation for this. I don't know if you guys know yet the equation, guys. This is a lot of physics involved, guys, by the way. But the idea is something that's known. Okay, so light, we know for a fact is a wave, okay? But sometimes what? It can act as a particle based on a what? Based on Einstein's photoelectric effect, and that is what he got the Nobel Prize for, okay? If you want to get into details, guys, we can talk about like, like in physics, okay? But like chem-wise, guys, I mean, we can talk about it, but what's more important, guys, here? So extreme quantum mechanics, guys. I don't know if you guys want stuff, guys, but so light can act as a particle or a wave. Okay. So what they're coming up with is this: particles, such as electrons, right? They can act as a wave. You know what that means here? So the question is what? The question is wavelength is equal to constant divided. So what it means is, guys, just so you know, that electron moving at a certain speed. Okay, I mean, like, it's a particle at a certain moving at a certain speed. But what they're saying is based on this equation, it's called de Broglie's equation. Is what? This electron can act as a wave. So that is the dual nature understanding of matter. Okay, so electron can be a wave. Okay, so that's the basically high level of this. So yeah, light can act as a particle and a wave. Okay, particle can act as well, guys. Wave and particle. Okay, it's a dual nature. Why am I talking about this? So I mean, this is something you have to know for if you can. Okay, and why we talk about it, guys? Quantum mechanics. So so the latest atomic model, okay, it's not Bohr's, right? It's what? Quantum mechanics. Quantum, like they use the term quantum for everything now. Quantum, like you got like what files like quantum speed, like so that's the pretty cool term, right? Quantum. So so quantum mechanics. This is the latest and best model that we have for the atoms now. Okay. So everything we talked about, like electron, like okay, acting as a wave, like stuff like that, like that, it's all incorporated. Okay. So the first thing first, guys. Let's talk about it. So the main idea of this, okay, quantum mechanics, what, guys? Electron is what? Is a wave. That's the main idea of this. Okay, electron is not a particle. Okay, did you hear the term, guys? Ever heard the term, guys? Electron cloud. Okay, that is what electron is a wave. Okay, electron is not like stuff that you probably heard, like oh yeah, electron, like Bohr's model, right? Electron moving circular orbit. That is not a thing anymore because why? They're thinking what? Electron is a wave. Okay, it acts like a wave. Okay. So there's a guy, guys, like a Heisenberg uncertainty principle. Okay, what did he say? We do not know where electrons are at. We do not know the speed of electron. Okay, this is like very detailed. That's why electron is what? It's a wave. Okay, and now this kind of explains. So electron moving in a wave kind of explain like Bohr's understanding of quantized interval. Okay, so hear me out on this. Okay, so this is a nucleus, right? So let's say, for example, guys, electron, like like has some kind of wave. Electron has some kind of wave. Okay. So let's say this is a wave for electron. Okay, it's a wavelength for electron. So you can't change that, right? Now, for example, guys, this is the first shell. Okay, the first principal energy level. So if you look at it, right? So so electron can be like one wave, two wave, okay, like three wave, four wave. Okay, so that's the first. So it's what? It's like electron moves in a wave. Okay, so that's the first shell. Okay, and now so the second shell. So why electron is not found anywhere between here to the next shell? Because that's based on the Bohr's model, right? So so the next shell. It's like this, okay? So now, I mean, it's I'm sure too big, but same thing, right? It's gotta be what? They have to be what? Fit a wavelength in there. So you cannot have like between the two wavelengths here, okay? So because it's a wave, guys, it must be at a multiple of a wavelength of the electron, okay? That's why anything between, you're not gonna find it, okay? So it must be, okay? So that's the reason why there's a gap there. So that's why, that's the reason why Bohr's understanding of the principal letters of always what? It's, oh yeah, there's nothing in between because electron moves like a wave. There must be a space because what? Wavelength, at least one wavelength difference should be added based on what? The circumference of the circle. That's basically the understanding of the principal letters of, guys, okay? So everything that we're going to talk about is what? Electron acts as wave. Do you have to know it's ready, PCAM, guys? I don't think so. So like the teacher who discussed or talked about like this, the waves, electron active wave, like going crazy on this one, guys, and the radial nodes and all. I had one teacher who did this. None of your school, by the way. So it was like Bergen Academy, I think. That's there. I don't know. So one teacher was going like doing this kind of stuff. So I had to show them this stuff. So again, I don't foresee like this from the schools that you guys like, from what I hear, guys. I don't think it's gonna go this crazy. But it's in the textbook, okay? So it's not in the reading probably I gave you guys, but it's in the textbook. If you guys read it, then you'll get it. So, but again, just quantum mechanics, guys. I mean, the high level guys for you guys to understand. His electron is what? Dude, it's a wave. Okay? It acts like a wave. That's a reason why we do not have to figure out where they're at. Okay, but like, okay, so but what they're doing with the electron is what now is what? They're trying to figure out, okay, so we don't know where they're exactly at, but what they're doing is what? They're trying to provide them with the address of the electron. That's called quantum numbers. So to figure out, okay, approximate position of the electron, okay, they're providing the electrons with quantum numbers. Yeah, so like for example, like you guys, right? Like I was using this example a lot. So like for example, your parents, right? Like they drop you off here or whoever drop you off here or whatever. So like they know you're in this facility, okay? But they don't know exactly where you're sitting, how fast you're moving or sitting down. They have no clue, okay? Same thing, okay? Electrons, we understand, we know that they're somewhere there, okay? The waves where the waves are at, but we do not know exact location or their speed, okay? That's the exact same thing. That's what we do. We give them address for each electron. And that's called the quantum numbers, okay? So the first number, guys, is what we call the principal interval. So like the shell, the first shell, second shell, third shell, blah, blah, blah. And then this one represents, guys, the second one represents a sublevel number. And this one represents, guys, orbital number. This represents spin. So this is basically, guys, like, okay, United States, New York State, like, whatever the county, the street name, whatever, that's basically what this is. Okay, so they're providing them with an address for the electron where they have a highest probability of being found. That's what this is. Okay? Instead of trying to figure out, oh yeah, they're like here orbiting the circular motion, now provide approximate location where the electrons can be found. That's what quantum mechanics is. Okay? Do you have to know the quantum mechanics for APChem? No. They don't ask this question. They don't ask, oh yeah, figure out quantum mechanics for this electron in this element. They don't ask the question. Okay? But you have to understand like what it represents, as at least what it is. Okay? Any questions so far? Let me know. So what do you have to know? You have to know, guys, first and first, I'm sure you guys already know this because you guys took guys, I don't know when. You guys have to know, guys, electron configurations. You guys have to know this. Electron configurations. Right? I mean, again, if you guys don't know it, guys, I really don't want to talk about it, guys, but this is important, by the way. Like 1 is 2, like 2 is 2, like 6 and stuff like that. That's what electron configuration is. Okay? That absolutely no question to know that, guys. Okay. So you have to know the electron configuration. This is based on the quantum mechanics. So again, You get what I'm saying, guys? Okay, again, the term orbitals. Okay, orbital is a region within the atom where there is a highest probability that electrons can be found. That's what orbital is. Okay, so keep that in mind. Okay, so the quantum mechanics is based on the wave model. Okay, which is what where the orbitals where electrons can be found. Dude, I can get into a little more detail, but there's no point. Like for you guys, AP Chem perspective guys, unless you take Olympiad or stuff like that, there's no point talking about it more. Like nodes and anti-node. Yeah, so. But now, do you anyone have a problem with this, guys? I don't know about this. You guys, I know some of you guys are rusted, I guess. If you guys did something else, let me know. For example, guys, like if the question is asking guys, find the electron configuration, guys, for like copper. Okay. So then if you guys go to copper, which is number 29. Which means like you guys have to kind of go in. Okay, so copper has 29, which means you know, this is on the, if you look at periodic table, guys, this is the first principal energy level, second level, third level, fourth level, guys, by the way. So, and this is the S block, that's the P block, and this is the D block, you know, that's the F block. So you gotta figure out, guys, the first principal energy level has what? Well, S sublevel only. The second principal energy level has what? S and P. Third principal energy level has what? S, P, and D. These are all what we call the sub-levels within the principal energy level, right? And the fourth one has what, guys? Fourth one has S, P, and D, and F. So it's got these principal energy levels, guys. You have to distribute electrons, you know, accordingly. So, guys, if you guys look at this, guys. And so one of the things you have to understand is what, guys? For the S sublevel, okay, they only got one orbital. Okay, it's got one orbital. So second principle is what, guys? S and P orbital. Okay, so which means like, okay, so S and P sublevel. So S has one orbital, P has three orbitals, guys. They have a total of what? 4 orbitals overall. So and then like if you look at this, guys, they have what? 9 orbitals overall. So D has 5 orbitals, by the way. So basically, guys, the bigger the number becomes, guys. I mean, so you can fit more electrons in there. So basically, guys, I mean, so there are 29 copper electrons in there. So copper looks like this, guys, 20, 29. So whatever this is, guys, 60 something, 65 or something, 63. Copper's got what, guys? 29 electrons. So how are you going to distribute these electrons, right? So you're gonna start from the inner shell to the outer shell, right? So it becomes what, guys? So 1s2, got that. So 1s, there's the first principal level S sublevel orbitals, and S orbital has one S sublevel has one orbital only. And again, each orbital can have what, guys? 2 electrons, right? So that's one of the stuff that you guys should definitely know, guys, from the regular chem. So that's why you put 2 there, because again, S sublevel has 1 orbital only, and each orbital, okay, 1 orbital can have what, guys? Can have 2 electrons, okay? So again, orbital, again, is what, guys? The housing for the electrons, okay? And the orbital can have what? Electrons, how many? 2 electrons. And now, so you gotta go to the next shell, which is what? The second shell now, because this is filled up. Okay, the 2s, 2, right? It's the same thing, right? So they can have 2 electrons overall. And now you gotta go to the next shell, which is the next sublevel, which is 2p. And again, P has what, guys? 3, okay, orbitals, right? So they can have the 6 electrons. So now, up until here, you have a total of what? 10 electrons overall. Okay? So 10 electrons, you put, out of 29, I put 10 in there. So you got the next shell, which is the third principal energy level. So 3s, 2, 3p, 6, this is up to now 18. So I gotta put more. So one thing to understand, guys, so again, D block comes a little later. So if you guys don't know what I'm talking about, guys, I can slow down a little bit because I mean, this is AP class, so I'm not like, you know, really doing the deep, like the basic stuff, guys. So the 3D comes later, 4 and 4s. So the next one becomes 4s2, and then becomes a 3D, whatever left over. 3D copper should be 3D9. I mean, that's a basic like rule. Okay, so, but again, you should know, guys, like 4s, it becomes 1, this becomes 10. That's a basic rule, guys. I don't know if you guys ever learned that, I'm not sure. But let me know, guys, if you're like, I'm not sure about this, but then I'll slow it down and practice more on this. Let me know, guys. Let me know. If anyone, like, I know some of you guys, like, you guys just done this, right? So I'm not sure. Yeah. So it can hold two, okay? But because, I mean, there's some uniqueness of copper. Copper sends one electron of the s to the v bar. Okay, so that's one of the exceptions we'll get to know for copper. Let me know, guys, again, I'm not judging you guys, so let me know, guys, who needs more practice on this right now before I move on to next stuff. We have only 15 minutes, so I'm not going to get too far anyways, but let me know, guys. Let's try, guys, some of the stuff. Let's try, guys, the electrical configuration, guys, of sulfur. Let's talk about, guys, the CR, chromium. Let's discuss I don't want to do something too big. CR. Yeah, so let's do these three, guys. I'm going to use some time, guys. So write the configuration for these guys. Okay. So give me, guys, what we call write full configuration full, which means, guys, you gotta write like 1s2, 2s2, 3. You can't abbreviate it. Okay. It's a couple minutes, guys. So sulfur guys, if you look at it, so I mean, again, the sulfur is right here. Okay, this is like the three P block guys, by the way. So it's the 1, 2, 3, 3 P block. So you gotta fill everything up with 3P. So it becomes 1s2, 2s2, 2p6, and 3s2. So it's gotta be filled to here, because like we're talking about here. So we're doing grassy here. So it becomes what, guys? So it has one. It's in the fourth one. So 1, 2, 3, 4. So it's what, guys? Like 3, P, 4. And that's basically how you do it. Okay. And now, if you add these numbers, 2 plus 2 plus 6 plus 2 plus 4, it should add up to the total number of electrons sulfur actually contained. So that's about 16 electrons overall. Any questions, concerns? I mean, it should be that bad, right? Questions? All right, next one, guys. So chromium, Cr. So chromium is right here, number 24. So it should fill everything up to here, which is this is a 4s, right? So if you look at it, guys, it becomes what? Same thing, right? So 1s2, 2s2, 2p6, got 3s2, 3p6, and that is what, guys? This is 4s, right? And you guys should know, guys, like 3d comes after 4s. This is 3d, guys, by the way. So it becomes 3d and what? 1, 2, 3, 4. Right there. And that's the ground state configuration, right? Like that's how you do it, like on a textbook, right? But now, one thing to be sure, just like copper, okay? The actual configuration for guys 4s1, 3d5. So one electron goes into this guy. Okay, because why? So listen carefully. If they ever ask you why they do this, okay? Why are they doing this and why are they doing that, guys? Your answer is what, guys? Your answer must be what? By moving electron from 1s to 4s to 3d, guys. So your answer should be, so with the electron repulsion. Okay. So by having electron pushed out to 4s to 3d, what happens, guys? Its electron experiences less electron repulsion. That's the reason why it's better to push out the electron to P1. So why is it that, guys? Because what? Whenever you can give 4 electrons to make it what? A half filled. If you got a half electron status like this, or fully filled, 3d10, right? So 3d10. So there is something about, okay, for you guys, just so you know, if the half filled blocks tend to be more stable than when it's not. Okay, so that's the reason why it's better to have what? Half filled D block versus what? Only like a portion filled in. Yeah. So that's the reason why this is like exceptional that you get to know, guys. I'm sure your teacher will talk about it. I'm this whole thing. So you gotta be watch out, guys. The line of CR, not everyone do that, but they'll only ask what CR. And line of what? Copper. It's one of the things you have to watch out for, okay? And now, BR. Okay, so if you look at BR, chromium, guys, this guy is like a lot of stuff. So it becomes 1s2, 2s2, 2p6, 3s2, 3p6, okay, 4s2. Okay, now this is all filled in, right? 3d10. Keep in mind, guys, 3d comes after the 4s. Okay, 1s is like next to 4s, right? This part, guys, also 4p5. Okay. That's the configuration for VR. Okay. Any questions, guys? I mean, dude, like, I don't think, guys, the electron configuration wise, I don't know. They really cannot ask you much of a difficult stuff. Okay. Just so you know, they can't ask you like crazy stuff on this. But now, one thing they asked, and I have seen students get it wrong, is stuff like this. Okay. For example, they ask you guys, find the configuration for Fe 2 plus. Okay. Do you see this, guys? Yeah. So again, if there's a 2 plus, what does it mean, guys? They lost the the iron lost what? 2 electrons. Okay? So figure this one out, guys, okay? So Fe2 plus, write the configuration for Fe2 plus. See what it is. Fe is on number 26, by the way, okay? To the right of the Cr, chromium. Okay. So let's take a look at this. Because one is 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, yeah? 1, 2, 3, 4, 5, 6, right? That's Fe, okay? This is Fe, right? But how do I do 2 plus? Okay, 2 plus means what, guys? They lost 2 electrons. So I tell you, okay? So you gotta remove 2 electrons. So what you're probably thinking is what? Is it gonna be this guy or that guy? Right? That's the question, right? So will it be 4s that you're gonna take electron out or 3d? That's probably the question you're asking, guys. Whenever you're removing electron from metal, okay, it always must be the outermost shell first. The 4s2 gets out first. As well, guys. It'll be 4s0. Okay, so this is the configuration for Fe2 plus. You don't have to put the 4s into it. Okay, that's the configuration. You understand, guys? Here. So I understand, guys. I mean, you're moving the electron. You're putting the electron lastly on the 3D block, but when they're losing electron to react, they lose the electron from the outermost, the 4s first. Okay, that is one of the questions. 2015. Okay, FRQ number 1 for the AP Chem. And there's some screenshots. And you gotta find out. It's definitely there. So I think 1 like E or something. No, it's the last question, guys. And I haven't seen, like, I saw so many students got this wrong. Okay, for whatever reason, I'm not sure. Any questions, maybe? Question, concerns? Let me know. All right, so this is, guys. I mean, I don't know. In terms of the quantum mechanics, guys, I mean, that's the most they push, really, guys. Because they don't go they don't ask a lot of questions on the quantum mechanics portion. The other thing they ask that really isn't in a lot of the school teachers agenda, which is on the AP lot, guys. Something about binding energy. Okay, so binding energy. So this is, I don't know, time-wise, guys, I can't do it right now. So what's remaining for us to discuss on this topic, guys, is binding energy. This is something that is not easy to do. It's on the AP only. Okay, it's the AP only, guys. It's not that hard. It's just a concept you have to understand. And then after this, guys, we have to discuss periodicity. That's the next one. Okay, so this will be something we'll discuss by next week. Okay, for AP Chem. And then the unit is over. I'll assign the homework for this, guys, for this chapter. So probably this week, guys, for your homework, guys, homework is just to review, and you can. There's a question in the back of this chapter. Okay, you can solve it if you want to. Okay, we can just, if you have any questions on that, we can talk about that. So, but that is not the homework. Okay, that's only whether you want to do a little more with the chapter. Okay, look at the question in the back. Okay, but the homework assignment should be probably something I'll assign next week. Okay. So that's gonna be online homework, not the homework. Yeah? Okay. So as so again, please do the homework, guys. Read the chapter, and we'll discuss next week. Okay. And if you can't make it on one of the classes, guys, please let me know prior,